Welcome to an episode of Blinded by Science, starring Neva and Maddie here. Yeah!
Alright, I'm sure you're wondering, what does a bowl of ice water, a tomato, and a biscuit with lipstick on it have to do with science? Well, Neva is here to explain.
I'll tell you why. This is what it has to deal with. The Charles Law, and it's one of the gas laws that we're going to view today.
Awesome! Let's get to work. Alright, well, the first step in our experiment is to figure out the temperatures. Well, we know the room temperature is 70 degrees Fahrenheit, but what is the temperature of that?
Well, I'll tell you, Maddie, but you're not going to like it. We're going to use this handy-dandy probe.
No!
Oh, yeah. Ready? We're going to stick it in the water now.
So, what is this probe doing?
Well, as you can see here, Maddie, we're going to get the temperature because it's cool. As from room temperature, it was 70 degrees Fahrenheit, but in the ice water, it's obviously going to be colder. So as you can see here, the temperature is moving slowly down. Moving slowly down.
Oh my gosh, I can see that. That's amazing. So, I think that's the temperature of the water.
So Maddie, from what I can tell here, is that our probe is doing its work on this ice water. So as you can see here, on our probe, it's telling us that it's 35 degrees Fahrenheit for the ice water.
I see. Thank you. Step 2 is to put that tomato in that ice water. Neva?
Maddie, I am taking this tomato and I am placing it in this ice water, slowly.
Well, it looks to me like that tomato is in that ice water. Let's check back in 20 minutes. New, 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 new.
Maddie, what time is it?
Well, let me see. Wow, it's 20 minutes since when we last checked in.
Let's check on our tomato.
Let's do that. Looks all red. You got that tomato. Ah, too close.
As you can see here, it seems like the tomato has shrunken by the wrinkles that it can make.
It looks squishy too.
And very squishy.
So, this is proof that if you decrease the temperature, then the volume also decreases. Right, Neva?
Exactly, Maddie.
Yeah.
And this proves Boyle's law.
Look, Neva, I think Miss Biscuit is trying to tell us something. Oh, it's Charles' law.
So, Charles' law is volume divided by temperature of the initial equals volume divided by temperature of the final. So, what we know about our tomato experiment is that initially our volume equaled 200 milliliters. And it was 70 degrees Fahrenheit because of the room temperature. We don't know what the volume is after we change the temperature to 35 degrees Fahrenheit. So that's what we're solving for. We're solving for the volume. So how do we do that? First, we have to get the volume into liters. So Maddie, how do we go from milliliters to liters?
Well, you divide by 1,000, right?
So that would give us 0.2 liters. Okay. So now what about the temperature, Maddie? Do you know how to do that?
Oh, goodness. Going from Fahrenheit to Celsius, we have to subtract 32 and then multiply by 5/9. And that gets us to Celsius. But then we have to add 273 to go from Celsius to Kelvin.
So we're going from Fahrenheit to degrees Celsius to Kelvins.
Right.
Okay, so let's do that on the calculator.
Alright, so we have 21.11 degrees Celsius, but now we have to transform it into Kelvin. How do we do that?
Well, I'll tell you, Maddie.
Even though
So we have Kelvin is equal to degrees Celsius plus 273. So all we have to do is add 21.1 plus 273.
Alright, what do we get?
294.1.
Okie doke, so now we know the initial volume and the initial temperature.
Now we have to do the same for the final temperature, which is in Fahrenheit as well. So we have to bring it into Celsius and Kelvin, just like we did for the initial temperature.
Okay, sounds good. Alright, so we have 1.67 degrees Celsius, and now we have to move it into Kelvin.
So we do the same thing, and we just add 273 to 1.67, which
Okay.
is 274.67.
Ah, nice math skills there.
Yeah, definitely.
So, now that we have everything in the right units, we can put it into the equation. So, the initial volume was 0.2 liters over 294.1 K. And then, we don't know the final volume, but we know the final temperature is 274.67 K. So, if we move the 274.67 to the other side, it's 274.67 times 0.2 over 294.1, which equals
0.1867.
Alright, so the final volume was 0.1867 liters. And this concludes Charles's Law. And we're back with Neva, Miss Biscuit, and a giant purple ball. And we are here to prove Boyle's Law, that volume and pressure influence each other. But Neva, how are we gonna do it?
Well, I can say we want to use Miss Biscuit's weight, but why can't we use Miss Biscuit's weight and not mine?
Wait. Why, Neva?
Well, when I sit on this ball, my weight is going to affect the pressure and the volume somehow.
Well, why can't we use Miss Biscuit's weight?
Good idea. Why can't we use Miss Biscuit's weight?
I don't know, that's why I asked.
Well, the ball has its own unique pressure. And if I put Miss Biscuit on top of the ball, you see how the ball isn't affected whatsoever.
I see that.
Because Miss Biscuit's weight is less than the pressure inside this ball.
I see.
But my weight is way more pressure affected on this ball.
All right, let's see what it's gonna do.
Okay, Maddie, here I go.
Whoa, the ball is flatter. Okay, look how Neva's weight has increased the pressure on the ball, so the volume decreased. Now, look as the pressure decreases. Now increases. Now decreases. Now increases. Whoa!
Whoa! And this proves Boyle's Law.
Miss Biscuit, you're covering up the next law. What does it say? Oh, it's Boyle's Law. Let's explain. So, let's say before Neva sat on that ball, let's say it had a pressure of 5 psi and a volume of 600 inches cubed. And then, once Neva sat on it, she increased the pressure to 11 psi, and we'll find the volume. But we should know that the volume should decrease because as pressure increases, volume decreases, and vice versa. So, we know that the equation for Boyle's Law is P times V equals constant. So, let's try to convert 5 psi into atmospheres. So, after looking on the internet, I have found that if you multiply 1 psi times 0.0680459,639 will get you 1 atmosphere. Alright, so let's multiply it out. So, we know we have 5 psi times that big string of numbers there, and that will get us at the atmosphere the pressure that the ball was at. Go for it, Neva.
Check out that number, Maddie.
Whoa now. Alright, so through Neva's computations, we now know that we had 0.34 atmospheres. Yeah. Now, let us try to go from 600 inches cubed to liters. So, we know that centimeters cubed equals a milliliter. So we have to go from inches to centimeters to liters. Wow, that sounds complicated. Alright, so once again, after looking at the internet, I know that 1 inch is 2.54 centimeters. Oh, sorry. Okay, so let's multiply 6 inches squared, cubed, 600. So we know 1 inch cubed equals 2.54 centimeters cubed. So let's multiply our 600 inches cubed times 2.54 to get our centimeters cubed. Back to the calculator. Okay, so if we have 1,524 centimeters cubed, we have to divide by 1,000 to get it to liters. If we have 1,524 centimeters cubed, and we know that 1 centimeter cubed is equal to a milliliter, we have to divide by 1,000 milliliters to get to a liter. Leaves us with 1.524 liters. Okay, so now we have the initial pressure and the initial volume. But now we have to transfer the 11 psi back into atmospheres. So let's do what we did to 5 psi again. So it's 11 times 0.08459639, which gives us alright. So now we know the initial pressure, the initial volume, and the final pressure. So let's stick it in the equation. So pressure. Okay, so we know that the equation is P1 times V1 equals P2 times V2. So let's plug in the numbers. Pressure 1 was 0.34 atmospheres times 1.524 liters equals, our second pressure was 0.74 atmospheres times the volume we don't know. So we divide each side by 0.74 and we calculator it out. What do I get, Neva? So Neva, what did you get?
Maddie, this is what I got. 0.7 liters.
Awesome. Okay.
This concludes Boyle's Law. Do-do-do. Do-do-do.